orbits, and the planets themselves are amazingly round. The moon, for instance, is just almost perfectly a round ball. It is spinning so slow there's very little bulge at the equator. The Earth is spinning a lot faster, and there's about a 20-mile bulge. The equatorial diameter is 20 miles farther than the polar diameter. If you spin a basketball real fast, it'll flatten out like a frisbee. You'd have to get it really fast. But the Earth is spinning once a day, which flattens it out a little bit, pulls the poles in, sucks the equator out, about a 20-mile difference, which really is nothing compared to 8,000-mile Earth. You know, from space you can't see that 20-mile difference. The moon is, I don't know what it is, like 1 or 2 or 3 mile difference. It's very little. The moon is spinning once every 29 days. It also goes around the Earth once every 29 days, which is why we never see the other side. As it's turning, it's always facing us. You know, they never see the other side of the moon unless they go out there and take a picture with a rocket or something. But the moon is going around the Earth once every 29 days. The moon is almost perfectly smooth. The theories of how we got the planets and the moon all fall apart. There's the most common theory, I think, probably the most common theory now, is called the accretion theory. They will say the planets formed after the Big Bang, all these particles flew out, and then they all started drawing together because of gravity, and the more mass you get, the stronger gravity becomes, and they start sucking in particles, and pretty soon, you know, you got a planet. Well, you'd have a clump of rock stuck together. What's going to cause it to melt into this perfectly smooth ball? And so their answer to that one is, well, meteors hit, this supplies heat and energy. And that's what melted it. Well, there are some marks on the moon, but the moon is in an almost perfectly circular orbit around the Earth. And it's almost perfectly round. I mean, I don't think that's going to form by an accretion of particles over billions of years. Now, if you want to believe that, that's fine, but that's not science, that's religion. That's what they believe. And that'll be their answer to this one. But the moon goes around the Earth, but the moon is gradually getting farther away. We're slowly losing the moon. It's leaving us. The numbers vary. Now, people argue about this. There's good articles about this here. The impact article from Institute for Creation Research. If you want to get some fascinating reading, these little impact articles, they're just one-page articles. They're 10 cents a piece, and they started them in 1974, I believe. And they're up to number like 350 now. So for $35, you can get all of the back issues. And it is just amazing reading. I mean, that's an entire course in itself, just reading all the impact articles that they've put out for the last 25 years. This one is impact number 110, published in 1982, August of 82. And you can still, I think you can get some of these on ICR's website, icr.org. But they go through, by Thomas Barnes, was a University of Texas, El Paso. I've spoken there twice, done debates at University of Texas, El Paso. Matter of fact, recently, last month, yeah. He was a physics professor there. He was a young Earth creationist. And they didn't like him because they didn't want a University of Texas professor who believed the Bible. They tried all sorts of things to, ridicule him. He's now, if he's still alive, he's probably in his 80s. But I've talked to him a couple times on the phone. Really gracious man. He wrote this article 20 years ago about the young age for the moon and the Earth, showing that because the moon is getting farther away, that means, obviously, it used to be closer. Now, if you bring the moon in closer, you create a problem, because the moon is what causes the tides. Now, I don't worry about the tides here, even though I'm in Pensacola, because we're 60 feet above sea level. But the folks along the beach worry about the tides, right? I've been to the Bay of Fundy, and where the greatest tidal change, were you there too, weren't you? The greatest tidal change ever recorded during what's called a spring tide, when the moon and the sun both line up, and they're both pulling on the water. It was 103 feet difference from low tide to high tide. The water comes rushing in and out of that bay so fast, they surf in front of it. There'll be a wall of water 4 feet high. You can go up there and pay $5 and get in this big rubber raft. You were right there at the place, weren't you? And you sit for 3 or 4 hours. It pushes you upriver. And this wall of water, in this raft, just like going through the rapids, first you go out there and you sit in the mud, wait for the wall of water to come, and then they get a bus and bring you in the raft all the way back down to where you started. And here's your $5. We should go up there to the Bay of Fundy. Mom and I, a few months ago, were in Alaska, and we got to see the second highest tides, which is where Anchorage, Alaska is, which is where it got its name, Anchorage, a good place to anchor. But I forget the name of the bay now, but it goes up and down. That's the second highest tides. Generally, the world's tides, I think, probably average around 3 or 4 foot tidal change, from high tide to low tide. Pensacola here, it's not even that. It's probably only 2 feet. Very small tidal change. Other places, it's 50 feet. But the moon is causing these tides. As the Earth is turning under the moon's gravity is pulling on the water. This creates a squeezing effect. On the sides of the Earth, it squeezes in, and it pulls the water up on one side, and because of the squeezing effect, it pushes it out on the other side. So you actually end up getting a high tide on the opposite side from the moon. But the high tide on the other side is not quite as high as the high tide on the near side. If nothing was moving, just the Earth spinning, you would get a high tide every 6 hours. Or you'd get a high tide, 6 hours later you have a low tide, 6 hours later another high tide. It would all be real nice every 6 hours. But because while we're spinning around, the moon is also moving. And so you have two motions to consider. So the average is every 6 hours and 25 minutes you have a tidal change. Because in 6 hours, the moon has moved 25 minutes worth in its orbit around the Earth. Who cares, right? Okay. The point is, if the moon were closer, the tides would be higher. And we'll finish this one thought here and close on this. There's a law in physics called the inverse square law. And I want to put this on the quiz. What is the inverse square law? Be able to explain this. If two objects are attracted to each other, how strongly do they pull each other? Two magnets, let's say. If you get the magnets half the distance apart, you take the fraction 1/2, inverse it, and square it. It's now 4 times the pull. If you brought the moon back into 1/3 the distance, you take that fraction, 1/3, inverse it, that means flip it over, and square it. It's 9 times the pull. When you're measuring how bright a light is, my dad was an electrical engineer at Caterpillar Tractor Company. He was showing me all these charts and graphs they use. You got a bunch of people in the office, how much light do you want at the desk for the guy to work? Then you got to figure out how far away is your light on your ceiling, how many candle power does it produce, because if you double the distance, say I'm 5 feet away from that light, and it looks to be as bright as 100 candles. If I went 10 feet away, it'd only be as bright as 25 candles. Inverse, I think that's the right number, is that right? Inverse square? I have to do my math on that, but it would drop off as logarithmically as opposed to linearly. As you get closer to the light, you half the distance, it's 4 times as bright. You half it again, it's 16 times as bright. The inverse square laws, I will cover that in video number 6. They apply when you're dealing with forces involving magnets, gravity, light, and girls. When you half the distance, the attraction is quadrupled. A lot of guys don't understand that till it's too late, and we'll get into more of that later. But this inverse square law says if the moon were closer, the tides would be higher, much higher. The problem becomes worse the farther back in time you go. So the evolutionists have tried to answer this by saying, well, you don't know that the moon has always been moving away at the same rate. Good point. I don't. We do know it was closer. And if it's getting farther away, it used to be closer as you go back in time. This does put some kind of time limit. We cover in here evidence from space about the moon. This is which number? Number 5, page 11. You can get more information on this from source number 3, Scott Hughes, The Collapse of Evolution. Number 6 is Dennis Peterson, Unlocking the Mystery of Creation. And number 11, Walter Brown's book, In the Beginning, about the moon. Okay, back up one slide. So I'll ask you to explain what is the inverse square law. That's the law that says as an object gets closer, the gravity increases, the pull, the force of the increases as the inverse of the square of the fraction. That's not a good way to phrase it. Let's just say it like this. If you half the distance, it'll quadruple the traction. If you bring it into 1/3 the distance, it'll be 9 times the pull. And what phenomena does the moon cause on the Earth? The tides. Put that down. Heidi, is a quiz question. Also, actually, the moon causes what's called a land tide. As we turn under the moon, Pensacola lifts up about 2 inches. The entire city. We don't notice it because all of Florida is going up 2 inches. Goes up, goes back down. Called a land tide. Now, if you get a land tide going up and down, this can create stresses on the crust of the Earth a little bit and can trigger earthquakes or can increase the likelihood of them happening. Pardon me? How can you tell the Earth is going up? I don't know how they tell that. I'm sure there's ways.